All right. So we're finally in Unit 2, and basically, like I like to do here in AP Stat, I like to do an overview. I like to kind of hit on everything, and then eventually we can go back through and hit on all the little stuff. But I feel like lots of times these units, they're very big, and there's chunks of stuff, and it kind of overlaps in like two parts, and they kind of go together. So just like in Unit 1, I'm going to hit on most of chapters 7, 8, 9, and 10 are all going to be in here, sprinkled in, and then I'll go back through and we'll cycle back through and kind of see it all again. But we are going to be doing something called exploring bivariate data. So in this section, in general, we are going to be looking at scatter plots, correlation and linearity, least squares regression lines, residual plots. All right, we're also going to be looking at outliers and influential points, transformations to achieve linearity. And our studies so far, guys, they've been concerned with measurements of single variables, right? It's what we've been mainly concerned with, plugging in data into one list and seeing what happens, right? However, many important applications of statistics that we will be doing involve two or more variables that relate to one another. So it's not just plug into one list or one column and see what happens, right? They compare. So for example, if there's a relationship between the smoking histories of pregnant women and the birth weights of their children, is there? Many would say, yeah, okay. And many would be like, well, I don't know, let's find out. But that's two different things that we're comparing. We are comparing women who smoke and then birth weights of them as well. So we have to look at two different types of data for that. Is there a relationship between SAT scores and success in college? All right, some may argue yes, some may argue no, but you would have to look at both SAT scores and are those kids successful in college or not? Is there a relationship between the fertilizer used and the amount of crop harvest? Again, two different lists that you're going to have to compare to see the outcomes. Tons of stuff you look at, all right, is this way. Two questions immediately arise with this stuff, though. How can the strength of an apparent relationship be measured? I mean, they could be two totally different units that you're talking about again. How am I supposed to compare? How can an observed relationship be put into functional terms, right? So as in like, even if I can compare them, what am I supposed to do with them, right? Is basically what we're looking at. So for example, a real estate broker might not only wish to determine whether a relationship exists between the mortgage rate and the number of new homes sold in a month, but, all right, they might also find a useful expression with which to predict the number of home sales given a value of the mortgage rate. So this person might sit here and say, I don't only wish to determine whether there's a relationship between the mortgage and the number of homes sold, right? Is there a relationship? But maybe I can somehow create my own rough estimate, maybe a function, maybe a predicted scale that I can use to help give me a value for a good mortgage rate. A graphical display of that idea is called a scatter plot. You guys have done scatter plots before. A scatter plot is nothing new, but hopefully we get a better understanding than what you've seen in some of your algebra classes before. And it gives an immediate visual impression of possible relationships between two variables. That's what you're going to be using a scatter plot for. A numerical measurement known as a correlation coefficient is often used as a quantitative value of the strength of that relationship. So point being, how strong is it? How good is that relationship? All right. If you remember when you were doing these before, you'd find what we called a line of best fit, right? If you remember back to Algebra 1, and you'd find a whole bunch of points all over the place, and then you would do a line of best fit, and then we kind of be done with the problem, right? Well, what I'm implying here is then we have this correlation coefficient, and that tells me how straight and how accurate this line is. Like, is all the points kind of clustered in that kind of straight line? Is it pretty straight? Right? We don't know. It could be all over the place, which means maybe it's not linear. Maybe it's something else. These are the things that we'll get to. But either way, you try to make a connection. Evidence of a relationship is not evidence of causation, right? We try to make a connection. Again, evidence of a relationship If you're noticing a relationship in the data is not evidence of causation. We will come back to this idea later, but I just want to make sure that you see that now. So let's start taking a look at scatter plots. Suppose a relationship is perceived between two quantitative, so quantities. A relationship is perceived between two quantitative variables, x and y. So we're interested in the strength and direction of this relationship, right? And in any deviation from the basic pattern of this relationship. So I want to know, are all the points pretty close, almost practically in a straight line? Are they going up? Are they going down, right? I want to know what's happening with them. So we graph all the pairs. That's what you're taught to do in Algebra 1, and we examine whether the relationships can be reasonably explained with a linear function. Because the thing is, maybe they can't, all right? You're trying to guess that they can, but maybe they can't. So a tip, recognize explanatory as x and response as y as your variables in context. You've been doing this your whole life, you just haven't seen them written like this. Basically the idea of what you're plugging in and what you get out, like your response is what you get. So for example, we might be looking at a plot such as this. So just have a random one, right? Plots all over the place. And you draw your line of best fit right there. Sounds great, but how accurate is it? Should it be a straight line, right? Should it be linear, right? We want to take a look at all this. So we need to know what the term best fitting straight line really means, right? That we just made there. And we need to know how we can find this line. And we want to be able to gauge whether the relationship between the variables is strong enough so that finding and making use of this straight line is meaningful. Just because we find it doesn't mean that it's useful. Okay. So note, there are various lines of best fit, and we will be working with one called the least squares regression line, is what we are going to be doing. All right, it's called the least squares regression line. So there are patterns in your scatter plots, right? When larger values of one variable are associated with larger values of a second variable, the variables are called positive associations. Basically what I'm getting at is if I have a positive x and a positive y followed by another positive x and an even higher positive y and another positive x way out here, another positive y, it's a positive relationship, right? A positive association. Basically what I'm saying is the points go up, right? Positive association. The points are going up. That seems pretty obvious. When the larger values of one are associated with smaller values of another, then it's negative, right? Here, up, and then it starts going down. So larger values, but it's going down, then it is negatively associated, or the points are going down, right? The strength of the association is gauged by how close the plotted points are to a straight line. So the strength, the closer they are to a straight line, the stronger it is. The closer they are to a straight line, the stronger it is. Correlations may also be positive and strong, right? Because it's going up and it's strong. There you go. That's pretty close to a straight line. It's not quite a straight line, but I mean, it's pretty close. And it's positive. It's going up. Correlations may also be positive and weak. So it's looking like it's going up, but they're kind of all over the place. Point being is it's positive, but it's a little weaker because even though it's a straight line, it's kind of not going up the whole way. The same goes for negative, right? Negative correlations as well. Sometimes different dots in a scatter plot are labeled with different symbols or different colors to show different categorical variables, and the resulting labeled scatter plot might distinguish between men and women, or between stocks and bonds, or who knows what. But the resulting labeled scatter plots might distinguish between those two things, right? So my point is, you can have two scatter plots on one thing. It doesn't mean that they go together. They might go together within the same idea of the problem, but they are not the same thing. Maybe that's men and women. Maybe that's stocks and bonds. I don't know. That's the point. You're trying to figure that out. And the graph is labeled scatter plot and distinguishing mean with plus, it should be men with plus signs. There you go. Men with plus signs and women with square dots to show a categorical variable with each one. still see if there's a pattern or a straight line with either or. When analyzing the overall pattern in a scatter plot, it's also important to note clusters and outliers, right? So for example, let's say an experiment was conducted to note the effect of temperature and light on the potency of an antibiotic, right? One set of vials of the antibiotic was stored under different temperatures, but under the same lighting. A second set of vials was stored under different lighting, but under the same temperature. So here are the graphs. So this is the temperature and the potency of the antibiotics. And then here is the potency versus the light intensity, right? So we can see what's happening. And the point is, there's an outlier down here. For the most part, other than that outlier, everything seems to have a good pattern. And these are kind of clustered together, is the point. They are kind of clustered. So, taking a look at these, it says, in the first scatter plot, which is the temperature, note the linear pattern with just one outlier, and that far outside this pattern. All right, it's way down there. So maybe a fluke happened with it. Maybe it wasn't handled properly, like in your vial. Okay. A possible explanation is that the antibiotic is more potent at lower temperatures, maybe. For some reason, maybe when it's down here, it's real potent, and then magically at some turning point, it starts back up here and goes down. I don't know. But only down to a certain temperature at which it drastically loses its potency. That is one option. In the second scatter plot, which is light intensity, note the two clusters that we have. It appears that below a certain light intensity, right, below a certain light intensity, it is one value, while above a certain light intensity, it's the other. So as the light intensity goes up, for some reason, boom, it just switches over for some reason. Right? In each cluster, there seems to be no association between intensity and potency. Right? There doesn't seem to be an association between the two, as you were to look at that. Whereas with this, it seems to be that the temperature, for the most part, other than this little thing, it does appear to kind of decline as we go, other than that one little outlier. All right, and we'll get to that stuff. When I come back here, I will take a look at the correlation and linearity and see what happens with those.